Okay, exactly. Will we choose as this correlation decision 3y? Okay, exactly. Y is equal to zeros. Okay, exactly correlator. The BPSK diagram coherent deduction of this. This is absolute. Okay, coherent deduction. Subtractors will be subtract this information and the decision devices. We choose one for this. Okay, choose zero for this. Okay, right. Choose one for if the output is equal to this zero, one is equal to this is y is equal to greater than zero. Okay, choose one. Y is equal to less than zero. Choose zeros. Okay, right? So now let us take error probability. How to calculate the error probability of the binary functions? Look back. The x of t is the received signal. x1. Okay, exactly. x1 is equal to generated signal for the generated signal for a simple one with the help of the basis function f12, that is given by this equation. As you know, the output function is whatever the transmitted signal, there is s1 of 2 as a rest of 2 will be multiplied with the basis function, and hence output is also the basis function. That is why even the received information x1 as this is for x2 in the function of the basis function. When you come back to the x2, the generated signal for a simple 0 with the help of the basis function 0 to TB is this. Okay, right? So that means when you come back AWGN theory, look back here. Okay, so look back here. As per AWGN theory, the x2 is equal to the output signal, that is as per input signal plus noise in the AWGN channel. Therefore the generated output signal s1 of x1 of t for representation of a symbol is x1 s2 of t plus omega t generation, what you call it as, okay, generalized output signal to represent one. Okay, here, so this is for one transmitted signal s1 of 2 to represent the one with the frequency transmitted the frequency f1. s2 of 2 is equal to what exactly? Transmitted signal with s2 of 2 with the frequency f of 2, generated output signal to represent one. So from the BSK receiver, that is receiver, we know y is equal to x1 of 2 because we going to subtract that not to cancel out the phase. Phase is not necessary here. Okay, when you cancel out, let y is equal to Gaussian random variable, because you know that when the signal transmitted to the receiver, the signal in especially transmitted to the receiver through the AWG channel, there is a noise. Even though we have used AWG channel as a constant noise, but still noise will get affected. Noise will absolutely get affected. So the noise is a random in nature. So we need to representation with what exactly? The Gaussian random variable. Let us say output signal of each bit after the subtraction as a random variable, which is given by capital Y. In a similar manner, x of 1 and x of 2, which is a Gauss random variable for x1 of 2. This is for one value you have taken. So now capital, this is the sample. Small y is a one sample because so many information coming. Let us take for a one sample for which we have the Gaussian variable. So by statistic theory, the conditional random variable, given that symbol is 1. What is the conditional? By statistic theory, the conditional mean of the random y, given that symbol is 1, is given by, okay, exactly this is the randomness. Expectation y12 is equal to e is equal to x12. That is given that symbol is transmitted 1. This is e expectation. This is exactly random. This is absolutely given by mean of the value of the. If you say 1 is transmitted, expectation of the 1 is receiving that is given by this equation. E is equal to what? Square root of y12 is equal to e is equal to x1 of 1 minus e is equal to what? X2 of 1. Okay, exactly. But look back here, I mentioned it, x1 is equal to, that is the sample of small x. This will transmit with the symbol 1 with the frequency f1. As we know that as per the polar inertia equal, whenever the signal is 1 is symbol 1, it's transmitted with the magnitude plus square root of EB, and 0 will be transmitted with the magnitude of the what? Minus square root of EB. That is why when you say this value, when you say you are transmitting the message with the one messages, this becomes 0 and this becomes plus. That is why Ey is equal to minus plus square root of V. In a similar manner, the expectation of the Y with the given transmission, the mean of the transmitted message is only depends upon the signal is 0, then the signal is equal to minus EB. Okay, exactly like this. Okay, in a similar manner, variance. What exactly the variance? The variance is depends upon, as you know, AWG variance of the signal is only depends upon the noise, not only on the symbol of the transmitted. Therefore, variance of, okay, exactly, the variance of Y is equal to variance of Y is equal to variance x1 plus variance x2. That is variance. Variance is the parameter of the statistically which is defined noise get variance. Because signal is a constant, noise is the factor is only choices. Okay, so variance of the signal which is passing the AW region, which you have proved that only the noise is a variance fact, does not change us. Okay, exactly. Therefore, the variance of the random variable is independent of the signal, so that is given by this. So as I know that variance is depends upon only noise, the noise of the what you call noise, exactly, noise is only depends upon the x1 x2, which is absolutely depends upon n by 2 and n by 2. So the variance of the output signal depends upon n not only. So now it's correct. This is the variance and mean we calculate. The conditional probability density function of Y, conditional density function of that is a random variable is given by conditional probability is that we are sending the messages from the receiver, okay, from the transmitter, such a way that which gives the sending, okay, let me repeat that. The conditional probability density function of Y, it is the random variable which gives the probability of sending the perfect information, let us say 0. That is why the probability density function Fi of Y is equal to, given that the symbol is 0, which is absolute square root of what you call 1 by square root of 2 pi into experiment. Okay, this is the equation is given by, which you can see how did you got from the previous when we calculate a probability of 0 in a QPSK or BPSK or any kind, which you have seen that you can able to understand this. Only thing you should mention it here, the conditional probability density function of Y, it's only the random variable is given by, okay, given by the random variable is given as follows, but the conditional probability density function is the one which gives the probability of a sending message is correct. Okay, so now let us take the P10. This conditional probability P10, look back, very important here. This is only sending the information 0. Here P10 talks about the probability of a symbol error 0, detecting 0, even the information received is 1. That is called as P10. P10, which is absolutely given by as per statistic integral of 0 to infinity f prefix y is equal to 0 into dy. Okay, exactly. Similarly, we have P10, that means sending the information is 0 and detecting the information as 1, and that is we call it as P10. So we know what is exactly the Q function which I defined. Y plus EB is equal to square root of E1 xi. When you changing the integration by 1 by square root of this, so we'll get back to P10 as this. See, look back, P10 is given by absolutely the sending the real information is 0, but detecting the information is 1 at the receiver, which is equal to Q is equal to square root of EB naught by 2. Okay, so that is when you take the average of P, see, look back P10, which is absolutely made up of, which absolutely consists of EB is equal to what in 1 EB10, okay, EB01, okay, exactly consists of both the zeros, okay, exactly both the P10 and P01, okay, exactly P10 and P01, okay, exactly these are the symbol. Since P10, okay, consists of what exactly EB naught, this is 1 P10, P01 is another condition probability, okay, exactly. Okay. So when you take the average of this two, that means the value of this and this has to be, because P10 depends upon only the magnitude of the energy EB and not. Okay, exactly. Right? When you take the average of this, we'll get back to what? Average probability of a bit error. That is average probability or error of BPSK. We'll get back to what? Q by square root of EB and naught, which is also, as we mentioned, bit error rate of FSKs. Okay, exactly. So now let's go back non-coherent. Okay, so non-coherent orthogonal modulation techniques. What I mentioned is, see, understand that What is exactly the coherent deduction? See, coherent deduction is the one, whatever the signal is received by the receiver of the BSK, it will detect the signal. Okay, it will absolutely detect the signal into the parameter of frequency and phases of the signal, which is exactly called as what I call it as coherent deduction. When you say non-coherent deduction, absolutely it means that without consideration of the phase, detecting of the signal, we call it as non-coherent deduction, which is explained clearly. Why this happen? Why non-coherent deduction is quite useful? Because when you pass this information, when you pass the information from the transmitter to the receiver, the signal in the AWGL will get corrupted. In despite you use the AWG channel or you use the channel which is imperfect in nature. But there are factors which is really affecting. Number one, there are a factor, first exactly noise in the channel and uncertainty due to the randomness of the signal parameter along with the distance. Three factors. First factor is affecting the signal while flowing in the transmitter, that's the AWG channel, the uncertainty of the channel line. The second factor is what exactly? Randomness of the certain signal parameters like variance, mean, and turn. What is called third point is equal to what exactly? Distortion in the transmit medium. So this is the factor which is really affecting. So one of the important factor is that which you cannot control, that is a phase. As the signal is transmitting from transmitter to receiver, the phases of the signal, that is which contain the information, that is the signal S1 of S1 of it, will get affected, and hence this we cannot recover the phases at the receiver, but we can recover the information with the help of the amplitude deduction. That means the method of deducting the information by regardless of phases, we call it as a non-coherent deduction. Please mind it. What is coherent? Coherent deduction is the one which deduct the information with the help of the frequency or phases of the signal received at the receiver. Where exactly the non-coherent deduction, without regardless of the phases, what will happen? That received symbol will be received signal will be deducted the symbols with the help of the amplitude. That is exactly we call it as coherent. What is exactly non-coherent orthogonal multiplication? Let us say S1 of 2, S2 of 2. This is a signal we are going to send. After transmission from the transmitter to the receiver, G1 of 2 and G of 2 will be the received signal, but both are diagonal, but the phases of G1 and G2 will be different. Okay, that is why we call it here X of T, that's output of the signal. Output of the signal as for AWG, and input signal plus noise in the signal. So received signal is G1 of 2 instead of what exactly? S1 of 2, due to the phases get changes in the channel. That is why G1 of 2, SW of 2, G2 of 2 plus F2. WF. This is the equation, and how that equation absolutely here, that equation we will get back to absolutely called as generalizer here. What will happen? Yes, X, that is G1 of 2, G1 and G2 all will become absolutely at these cases. Okay, here the filter match, what will happen? It removes the what? It recover the S1 of 2 from the G1 of 2. Here in these cases, recover the S2 of 2 from G2 of 2, and envelope deductor, what will happen? Deduct the amplitude of the signal, what is exact amplitude of the signals here. Okay, exact amplitude of these two signals here, and it will be sample and will be compared with the threshold voltage, and it is decide if this is the output of this is called as L1. This is output of this path, we call it as L2. If L1 is greater than L2, if L1 is less than L2, what exactly? This L1 is greater than L2, or L1, if L1 this is greater than this, absolutely it means that the chosen is this value, that is this amplitude of the frequency. And if the L2 is less than greater than this, then the chosen values is exactly what? This value, and is called as. See, this is what exactly. You look back here, this working as same as a quadrature filter. What is exactly quadrature filter? There's a two path. First upper path we call as in phase, and second exactly we call as quadrature path. That means whatever we have seen, the generalized receiver used in a non-coherent orthogonal modulation techniques, which detect the signals without the checking of the what, without giving an importance, or in other words, without giving an importance for the frequency and phases of the signal received. Instead of that, it detects the symbol with the help of amplitude. We can symbol as same. This is called general receiver, which can be thought as exactly quadrature. Exactly, this is exactly a quadrature symbol. This is Working is absolutely same here. Same. This is in phase path. The upper path of the generalized receiver, upper path of the what exactly this. But only thing is what exactly here, whatever the received signal will be multiplied with the what phi of t and pi cap of t, which is a Hilbert function. So that means the phases of this and phases of the upper pass and the lower passes will be the 90-degree shifted, which is required for quadrature. That means whatever the generalized, okay, exactly this generalized receiver can be matched of the what you call quadrature. So that's almost 90% of the second, the fourth, third unit has been completed. Remaining little extent is there. Tomorrow I'll complete it and we'll meet tomorrow as for the class. Okay, thank you.